Okay, so in the next 1 hour and 20 minutes, I would like to discuss with you what is a major problem in the management of coastal areas. Saltwater intrusion is known to be a topical issue for many coastal regions. Saltwater intrusion is the infiltration of salt water from the sea, of course, into the land. And this is particularly concerning because it's contaminating the underground of the land, and it's impacting the vegetation, first of all, and then it's also impacting the human activities because in those regions where people rely on groundwater for freshwater provision. In those regions, and many coastal regions actually rely on groundwater, in those regions, saltwater intrusion is a concern because groundwater, if groundwater gets salted, of course, cannot be used anymore for civil use. So saltwater intrusion is a phenomena that is widely studied for this reason. And it's also very much studied because it's driven by human activities, as we will see. So anthropogenic impact favors saltwater intrusion, and for the reasons that we will discuss together. So it's extremely important to understand how humans may favor saltwater intrusion in order to be able to devise solutions. And the solutions are typically required to be designed by engineers. So it's a phenomenon that it's really important to understand and to understand the drivers. Saltwater intrusion is also favored by natural causes, not only human-induced causes. And for instance, tsunamis, like the tsunami that occurred in Southern Asia on December 2004, these tsunamis are indeed effective on saltwater intrusion because they are moving a huge quantity of salt water into the land. And also, besides the saltwater infiltration that comes from inundated areas, tsunamis, by basically putting a lot of pressure given by salt water on the beaches, increase saltwater intrusion directly from the sea, not only from the land. So when you get huge waves that are hitting the beach, of course, the pressure exerted by salt water on the sea bottom is higher, which means that the salt water has a higher energy to penetrate, to infiltrate into the land. So I think there is a nice video, which is linked on my website. I am now indicating it with the mouse, that explains the dynamics of saltwater intrusion, provides a nice introduction. Let's have a look at this video. And it's not much long. It's 1 minute and 45 seconds. I think it's worth looking together. So it's explaining in what way I leave you to listening. I'm not sure whether you are getting the sound or not. If not, just click on the video on your PC. But it is also instructive to see the figures, by the way, so you can also look at my screen. So you see that there is a push of fresh water from the land in the underground that pushes back salt water into the ocean. So basically what keeps the salt water into the ocean is the pressure of fresh water infiltrated into the land. But this pressure decreases if we extract fresh water through wells. You see the picture here. The well is extracting the fresh water, lowering the pressure of fresh water, and then you get the intrusion of salt water. And let's have a look at the next part of the video, which is more related to institutional reaction and countermeasures. Countermeasures include injecting fresh water into wells. Now let me go back just 1 second and keep the video fixed because I just wanted to discuss with you the essence of the phenomena. You see, I'm repeating. You have from the land, you have a flux of fresh water into the ocean. And this flux can take place through rivers, and you see the river in the upper part of the figure, but also through groundwater flux. Groundwater flux actually occurs in coastal regions very frequently because coastal regions are often characterized by permeable soils. And therefore, in permeable soils, you have infiltration. Infiltration means groundwater replenishment and groundwater flux through the ocean. Actually, the amount of water flowing into the ocean through the underground is very considerable. It's something that we don't see, but it's actually very considerable and important. So this flux of fresh water from the land, as I said, pushes back the salt water, it is depicted in green in the underground here, into the ocean. So there is an equilibrium between the pressure of the salt water from the ocean and the pressure of the fresh water from the land. This equilibrium is in the underground, and these two pressures are competing. And depending on what pressure prevails, you have the fresh water advancing and finally flowing into the ocean, or the salt water intruding into the land. In a natural situation, you see this figure is clarifying what happens. You have in the deep underground an interface between salt water and fresh water, and look at the shape of the interface. It is like a wedge. So you have an intrusion that is deeper in the deep underground, decreasing in proximity of the land surface. Now, what happens when people are pumping fresh water from the well that you see in gray, that is basically feeding a water supply system. So let's move forward in the video a little bit, and let's see what happens when you pump. Just 1 second, I'm trying to understand here. I think it is fine. A little bit back. So you see, when you start pumping, there is the level of fresh water into the ground that decreases, of course, because you are extracting water, which means that the pressure of fresh water against salt water decreases. So what happens is that salt water from the right is intruding because, again, of the decreased pressure of fresh water, until you get to a situation where the salt water gets actually contaminating the well. It gets so high and so inside that the well gets contaminated, and finally the well is closed. And this is something that is, of course, very concerning. And keep in mind that remediation from saltwater contamination is actually not an easy task. Remediation is something that is a bit complicated because once that the salt has contaminated the underground, it's a problem. So what is a possible solution? A possible solution is to revert this process, to inject fresh water into the well. This is a possible solution. Or there are other solutions that we will inspect. Okay, now let me close this. And let's look at the drivers now. So what are the drivers of saltwater intrusion? This is a schematic representation of natural drivers. They are depicted on a plane that is based on the two scales, the spatial scale and the time scale. So you see the temporal scale in the horizontal axis and the spatial scale in the vertical axis. So the spatial scale varies from regional to global, and the temporal scale ranges from 1 year to 10,000 years. And you see the natural drivers independence of their scale. So you have the tsunamis that take place on a very short time scale, and they have an effect that is typically concentrated in the regional to the local to regional scale. And then you have hurricanes. Their time scale is more extended, and their spatial scale is more or less similar. You have the drought. Droughts are important drivers. Why? Because if you have less rainfall, you have less infiltration, and which means that there is a lowering level of groundwater, which favors saltwater intrusions. And then there are climate oscillations. You see that, of course, the time scale is shifted towards global, and the temporal scale is a little bit longer. When you talk about climate, the temporal scale is from 30 to thousands of years. And then there is climate change. Climate oscillations are different from climate change. Climate change is meant to be a permanent change. Climate oscillations are meant to be cycles, and climate change gives rise to sea level rise. Sea level rise favors saltwater intrusion. And then there is subsidence. Subsidence is lowering of the land, which means that you have an effect on, of course, on saltwater intrusion, because lowering of the land means decreasing pressure of fresh water. Now, let's have a look at the human-induced changes, drivers. Again, same temporal scale and spatial scale. The spatial scale here is more extended, so the vertical axis is a bit compressed. So there is accelerated subsidence, because humans may accelerate subsidence through soil compaction, through gas extraction, through water abstraction. Actually, groundwater abstraction is another driver, which is effective because it's lowering the pressure of fresh water in the underground. There is also the land drainage, which causes saltwater intrusion. Why is this? Because if you drain the land, you concentrate the flow of water into the channels, and you decrease infiltration. If the land is not drained and remains humid, remains characterized by wetlands, then you have increased infiltration. This is why we say that wetlands are extremely important to preserve the ecosystem. And then there is river modification, because again, if we modify rivers, and typically they are rectified, we eliminate meanders, which means that the course of the river is shortened. By shortening a river, again, you decrease infiltration. We decrease the domain of surface water, groundwater interaction. And then there is a land use change, and of course it's affecting infiltration. And there is also possible increased climate change exacerbated by human intervention. These drivers, I think it is important to have the perception. This is something that can be asked at the exam, like what are the drivers of saltwater intrusion? And let's keep in mind the substantial difference between natural drivers and human-induced drivers. Okay, now these drivers are also schematically represented in this figure. If you look at this upper figure and then you compare it with the lower figure, you see the presence of the wells, which give rise to decreasing. They decrease, again, the level of groundwater, and look at the intrusion that takes the form of a wedge. We will see a mathematical explanation why the saltwater intrusion takes this form. Now, how can we predict it? How can we estimate the mode, the dynamics of saltwater intrusion? It is essential to understand how it takes place, and a model is very helpful. And the model is particularly helpful because this is a kind of flow that we can describe in a relatively easy manner. What is the reason? The reason why groundwater may be easier for some aspects is that it's a very slow flow. Being slow, it's not characterized by turbulence, or let's say it's not characterized by very short and micro scales. It is something that is happening very slowly. It's of course easier to describe. There is the counterpart that is related to the fact that we don't see it. So given that we don't see the flow, and in particular, we don't see the domain of the flow, it's a complication because, you know, the soil is heterogeneous, and we need to describe mathematically something that we can't see and is spatially heterogeneous. On the other hand, I mean, the benefit provided by the slow character of the flow, it's important. So how can we model this process then? We need to describe groundwater flow. And let me go down in this handmade figure. This handmade figure clarifies that what we need to describe. We need to describe a flow that is taking place in the groundwater, first composed by fresh water that infiltrates, which can reach an impermeable layer. And then we have to consider the drivers affecting this flow, the wells pumping water, the interaction with rivers, and also the interaction with vegetation, because vegetation and also the presence of humans, of course, they use water. Vegetation uses water, humans use water, and this makes the process a bit complicated to describe. And then we have to simulate the movement of salt water, and this is a flow that occurs in the underground. So what are the means that we have available? And let me increase here the font a little bit. What are the means that we have available to describe this flow in the underground? First of all, this is a fluid flow, which is governed by the law of physics. And in particular, it can be described by imposing conservation of mass and conservation of energy, precisely because it's a process that obeys the laws of physics. So these conservation laws, conservation of energy, and, as I said, conservation of mass, can be combined into the so-called Darcy's law. I think you probably already heard in your past studies about Darcy's law. It's the fundamental law to describe groundwater flow. It relies under the assumption of 1D flow, so one-dimensional flow. Flow in general is three-dimensional, which means that you have the velocity of water changing along 3 dimensions. Under certain assumptions, you can neglect the change along one of the dimensions or 2 of the dimensions. In particular, when you have a dimension or a direction of the flow that dominates over the other 2, you can assume that the flow is 1D, one-dimensional. So you neglect the change of velocity in the other 2 dimensions, and that the component of the velocity in one dimension prevails. This is very useful because reducing a process description from 3D to 1D helps a lot in terms of simplicity. And in particular, this assumption can be taken when, as I said, the flow along one dimension prevails. This frequently happens in the groundwater flow, and this implies that the distribution of pressure in each cross section of the flow follows the hydrostatic law. So let me turn into the graphic blackboard because I want to clarify what I said. So basically, if you have a flow dominating in one direction, this means that you have the component of the velocity that the velocity has a significant component only in this direction. So you can neglect the other two directions. And if you have a water flow in the groundwater that is taking volume of groundwater soil where you have, and let's suppose that this flow is characterized by a velocity that is coming out from here, which is dominant along one direction. Perfect. This means that if you cut this flow with a plane that is perpendicular to the velocity vector, you obtain this section here. I obtain this section, which I'm now highlighting, by, again, cutting the flow with a plane that is perpendicular to the velocity. This is called, this section here, is called cross section of the flow. Cross section of the flow, perfect, of the flow. And here in this cross section, I can apply the hydrostatic law. What is the hydrostatic law? Hydrostatic law. Now, let me refer to this cross section and let me depict it here. And let's suppose that this flow is characterized by, in the upper part, by atmospheric pressure. This happens when the underground is permeable and there is no confining impermeable layer above. So it means that I have atmospheric pressure over the water. And let's indicate the height of this cross section with capital H. Okay, let's suppose that here at the bottom we have an impermeable layer, so the flow cannot infiltrate. Very good. Now let's assume that we have a fluid particle here. And let me indicate with lowercase h the depth of water above the particle. This means that, as we know from fluid mechanics, the particle is subjected to a pressure P, which is equal to gamma times lowercase h. Good. Now, if we want to express the potential energy of this particle, let's suppose that we neglect the kinetic energy because the flow is very slow. So the component of the energy related to the fact that this particle of fluid is moving, let's assume that is negligible. If we want to express the energy of this fluid particle, then we reduce to the potential energy. The potential energy is given by let's indicate with respect to a reference plane that I assume it's located in the bottom of the aquifer. Let me indicate the elevation of the particle with Z. Okay, so I am computing the potential energy with respect to a reference plane Z equals 0 that is located in correspondence of the bottom, the impermeable layer. Now I can say that the energy is given by Z, elevation of the particle, plus the energy pressure. So this is equal to Z plus P, pressure, divided by gamma, specific weight of water. This is equivalent to Z plus P can be written as the product of gamma H divided by gamma, which is equal to, I go here, Z plus lowercase h, which is, of course, equal to uppercase H, which is constant. Why it is constant? Because this is free water surface at zero pressure, which means that it's horizontal. This is, so the hydrostatic law. The hydrostatic law says that Z, elevation of a fluid particle, plus P divided by gamma is equal to constant. Okay. So this hydrostatic law is applying, is valid for groundwater flow 1D. 1D, okay? For 2D water flow, this is not valid. But for the groundwater flow, 1D groundwater flow, we can assume that the hydrostatic law applies. The hydrostatic law is particularly interesting because it allows to compute the pressure that the water is computing on a fluid particle. And the pressure that is exerted by a column of water over something, in this case, a fluid particle. Why I am interested in computing the pressure? Because we have two fluxes of water that are competing in the underground, and therefore, to understand who is dominating, I need to compute the pressure of fresh water, the pressure of salt water. So the hydrostatic law helps me in computing this pressure. Okay, now let me go back to my website. Darcy's law. The Darcy's law, I think it is interesting, an interesting discussion to see how it works, but I anticipate that in our subsequent discussion, we will not use it. In general, a groundwater flow model needs to be applied with the application of the Darcy's law. We will make some simplifications in order to get an idea of how the process is evolving, and the simplification will lead us to not to use the Darcy's law. But in any case, I want to briefly discuss it with you because it's a fundamental law for describing groundwater flow. It's the law that you should use through a model if you really want to describe in detail what's happening at the interface between fresh water and salt water. Now, the Darcy's law is expressed in this way. You see here, I make a selection. The flow Q per let's say, units of volume per unit time in the groundwater, one-dimensional flow, so which means that the direction of this flow is already known. What is missing is the amount of the flow, which we express in volume per unit time, is equal to the product of three factors. The hydraulic conductivity, which has a unit of velocity, units of velocity. the cross-sectional area of the flow, we already discussed what is, times the gradient along the direction of the flow of the hydraulic head J. The hydraulic head is, if we neglect, it's the energy of water. If we neglect the kinetic component, is given by the potential energy that we discussed before. This energy along the direction of the flow is decreasing with a gradient. The higher the gradient, the higher the flow. And this is reflected in the Darcy's law. If we call the hydraulic head with the letter capital H, the gradient can be expressed as the derivative of capital H with respect to the direction of the flow. X here is the flow curvilinear coordinate. Very good. Now, here you see that for a groundwater body, if you neglect the kinetic energy, the hydraulic head of an arbitrary fluid particle is given precisely by what I said before, is given by ZZ plus P divided by gamma, where P is pressure. Now, let's make an example of application of the Darcy's law, so we understand. Let's emulate the water flow through a medium. The medium here is given by the white rectangle. Above the medium, which is a permeable medium, we have a column of water. And I keep the height of the free surface of this column of water constant. Given that I have some water infiltrating through A, through the medium, I need to refill this column of water continuously to keep the, let me just decrease a little bit, to keep H3 constant. Sorry, just 1 second. I just went back to the previous page. Just let me go back here. And I think I should better visualize the figure in a separate page. Here, okay. Very good. So I want to keep H3 constant. What is H3? Is the elevation of the free surface in the water column with respect to a reference plane, which is here placed in the bottom of this pool. Let's see later what is this pool. Okay, now the column of water is infiltrating through the medium. The medium has a cross-sectional area of A, and then the water that is coming out from the medium is collected in this bottom pool, and the water that is left free to overflow, so that the water level in the bottom pool is kept constant. Very good. So what is the gradient of the hydraulic head? Now, the hydraulic head in the upper pool is precisely equivalent to H3. Why? Because if you compute the hydraulic head at the free surface, you have zero pressure, so it's clear that the head is given by the only elevation H3. Perfect. For the hydrostatic law, this hydraulic head is constant through this pool. So the hydraulic head that you have at the free surface is the same hydraulic head that you get at the interface between water and the medium. Very good. So H3 is the hydraulic head at the top of the medium. At the bottom of the medium, the hydraulic head that you have is precisely H4. So the gradient is H3 minus H4 divided by what? Divided by the length of the path in the medium, which is L. So what is how I can compute Q? I have to compute the gradient. the gradient of the flow, H3 minus H4 divided by L. Let me go here again. H3 minus H4 divided by L times, according to the Darcy's law, A times K, hydraulic conductivity. And you see that dimensionally it's perfect because Q is volume per unit time, like cubic length volume divided by T time. Okay. Here I have K is the dimension of a velocity, length divided by time. A is length square. So the product of K and A is cubic length divided by time, which is the same as Q. In fact, here, this product here, this ratio here is adimensional. It's length divided by length. Perfect. So this is an explanation, an application of Darcy's law. Actually, this is the original experiment made by Darcy, who derived the law empirically. Then the law can be proved by coupling, as I said, conservation of mass and conservation of energy. But actually, the first derivation of the law was empirical. Perfect. Now, how can we use this to describe saltwater intrusion? By writing a model based on the application of Darcy's law of the aquifer. This is a bit complicated because you need to describe at fine spatial scale, because the medium is heterogeneous, you need to describe hydraulic conductivity, you need to describe the geometry and therefore the extension, the value of A, and also you need to describe the hydraulic head, which in turn depends on Q. So it's a bit complicated, of course, and for this reason, this is an application that is frequently done through numerical models and by using softwares that are already prepared. Okay, so now let's study the problem in a simplified way, because this is typically a process that is not stationary, so it's dynamic, it's changing in time, and the flow is continuously changing in time. Now let's simplify the treatment by making an assumption of stationarity. So let's suppose that everything is fixed in time. And in this case, the treatment can be simplified. Now, the scheme that I want to model is this, as I already described before. There is the sea on the left. There is an aquifer that is flowing into the sea. And there is, there might be a substratum, and there is an unsaturated zone above. Okay, very good. Now, let's now assume that we have steady state conditions, and therefore that there is no mixing. Steady state condition, I already said. Let me make a second assumption. Let's assume that there is no mixing at the interface between salt water and fresh water. So let's suppose that the separation between salt water and fresh water is through a surface which with no mix. Actually, this is a simplification. It's a second simplification because, of course, you have mixing. In the interface between salt water and fresh water, there is some mixing. But let's suppose that this this surface, is separating the two waters without mixing. Okay, very good. Now, if we make these two assumptions, we can readily estimate the position of this separation surface. Let me go again to the graphic blackboard. And let me open a new one. Okay. Now, let me make another scheme of what we have to describe. So let me change the color here. 1 second. Let me start with something close to brown. 1 second. Okay. Here. And let me increase the size. Okay, and let me start from here. So what we have is land entering into the ocean. Okay. Oops. Okay, that's fine. Let me now change the color back. And let me use the red color for indicating the salt water. It's not, of course, it's not really a realistic color, but we wanna, this is the sea. Okay. And now let me use a blue color to indicate the fresh water. Oops. It's not yet blue. Here, blue. Okay. Very good. Now let me continue. Let me extend the height of the sea level also on the right part of this graph. And let's suppose that we have here a bottom layer, which is not really needed, but this should be horizontal. Just 1 second. Let me make it horizontal. Perfect. Now let me decrease the size, otherwise I cannot easily write. Okay, 2. Now let me indicate with capital H the height of the sea level with respect to this reference plane. So this is capital H. And this is z equals 0. Okay, reference plane, arbitrary reference plane. And now let me consider a certain separation, separation between salt water and fresh water. Just 1 second. Let's put here red again. So let's suppose that we have a wedge like this. Let's suppose that we have a wedge like this. And now let's refer to this fluid particle here. Perfect. So what is the pressure of salt water on this fluid particle? It is a pressure that comes from the sea and pushes into the land, of course. This pressure can be given by the height of the column of salt water, H, times, let's indicate with gamma S the specific weight of salt water. Now, what is the pressure of the column of fresh water? First, let me indicate with here lowercase hf, the height of fresh water with respect to the sea level. So the pressure here by fresh water will be given by h plus lowercase hf times gamma fresh. And the two pressures are equivalent. Why? Because the fluid particle is sitting on the separation surface. Of course, if the pressure of salt water would increased, then the particle will move into the land, and the separation surface would move into the land. But in this case, given that I assumed that the particle is sitting on the separation surface, it's clear that the two pressures are the same. What is my unknown here? I am interested in the value of capital H, because it tells me how much deep is salt water with respect to the altitude of the sea level. So if I make a well here, I need to know this depth, capital H, because I don't want that the bottom of the well goes into salt water. So I am interested in this capital H, so let me find an explicit representation for it. Capital H times gamma S is equal to capital H times gamma F plus lowercase h f times gamma f. Good. Now I can write that capital H times gamma s minus gamma f, because I am bringing on the left hand side the first addendum at the right hand side. Okay, and this is equal to lowercase h f times gamma f. Now I am almost ready. H, capital H, is equal to, at the numerator, h f times gamma f divided by gamma s minus gamma f. Now let's give values to gamma f and gamma s, and gamma f is, as we know, is 1000 cubic meters per kilograms times cubic meter. Gamma s is a typical value for average salinity is 125 kilograms cubic meters. Good. Now here we can write that this is equal to gamma f is 1000 divided by the difference between the two, 25. HF. This is more or less 40 HF. Perfect. What we wanted to compute is precisely this relationship. If I knew lowercase hf, and this is basically known because I can monitor into the wells the elevation of fresh water above mean sea level, so this is known, then I know what is the value of lowercase h, which is 40 times uppercase h. I know the value, I can compute the value of uppercase h, which is my unknown, which is about 40 times lowercase h f. Now, some considerations. First, you see that it is indeed interesting to see that if I get, for instance, an elevation of fresh water, which is 1 meter above the mean sea level, I can push in the deep ground salt water of 40 meters. So it really matters if I have an elevation of fresh water above mean sea level in order to keep saltwater intrusion limited. And it really matters if I have even a small change in lowercase h, f. So I have to be very concerned because with a small change, I can get an increase of saltwater in the underground that is very significant. So you understand that if I put a well here at this depth, for instance, this is my well, and this well causes a decrease of here a decrease of the freshwater elevation, you know that this is maybe a big problem because I may get, sorry, let me change the color. I may get a contamination of the well itself because here I would get a surface of separation that may become like this one, which means that here I get contamination. So this is under the assumption of steady flow, steady situation, and under the assumption of one-dimensional flow, which allows me also to draw this picture into a plane. It is a very simplified treatment, which however gives an idea of how it evolves. This result is the same derivation is reported here, I think with the same symbols. And I think there is also a sketch. Let me see here. You see, it's a little bit different, sorry. And the symbols are more or less the same, but with a small difference in lowercase h. I indicated the height of fresh water with lowercase h f. Here it's indicated with only lowercase h. So be patient, there is a small difference in the symbols, but you see the sketch is the same. Very good. So this is, sorry. Let's think back at the assumptions that we made. First, we assumed that the brackish zone, as we said before, between fresh and saline groundwater, it's an interface with a sudden change, and this doesn't happen. So actually, there is a transition zone between saltwater and freshwater. Let's take it into account. Second, the principle assumes hydrostatic equilibrium, whereas in reality, the aquifer might considerably deviate from this equilibrium assumption. And therefore, you know, if there are deviations, for instance, because some wells are pumping more water at certain times, you have to take it into account. And there are other figures which are depicting with a more colored representation what's happening. And I think there is also another one, and later on. But let's first discuss the factors that affect, with more detail, the factor that affect the saltwater-freshwater interface. And let's discuss in detail how these factors may make our assumption unrealistic. Our assumptions are realistic. So we already discussed the rising of seawater level, and it may be caused by land subsidence or ice cap melting after climate change and thermal expansion of seawater after global warming. This is another very interesting effect. Global warming affects sea level rise not only through melting of the ice cap, but also through expansion of the fluid in the ocean. There might be change in precipitation, and we already discussed it, lower infiltration, and therefore lowering the water table. We may have increased evapotranspiration, maybe due to global warming, but keep in mind that there is no consensus on the effect of global warming on evapotranspiration, but still there are several theories predicting that the vegetation may increase evapotranspiration, therefore ending up with more extraction of water from the underground by the vegetation. And then at the regional scale, again, we may have subsidence, we already discussed it, local climate change, but also urbanization. Urbanization is reducing infiltration, and this is something that may affect the process. And keep in mind that now we know that even a small change in groundwater level may cause a significant impact. And it's in several coastal areas, you have a combination of these effects. You have urbanization, which means impermeabilization of the soil, and you have groundwater withdrawal, because when you put people in the coastal areas, besides urbanization, you need water to feed them, and therefore increased water pumping. And here you see other sketch which summarize what's going on. And here is another one, etc. There are several of them. I found several pictures and several sketches because this is indeed a very relevant problem. Because, as I said, remediation is not easy. Now, how can we prevent this phenomenon? How can we mitigate saltwater intrusion? One way is monitoring, and there are several monitoring programs that are running in coastal areas. Here in my lecture, there is an example. The example is the monitoring stations in the delta of the Po River, close to Ferrara. There are several monitoring stations into wells and into the branches of the Po River, because saltwater intrusion may also happen along river. So you have, if you have a decreased flow into the river, which is more concerning during the summer, of course, you have salt water flowing back into the river, and then from the river infiltrating into the underground. So the monitoring station also need monitoring programs, also need to monitor the salinity of rivers besides salinity of wells. And how can we also prevent, this is, for instance, a picture depicting the situation, the salinity, the progress of salinity along the Po River in a particular date. It's 9 August 2012. And what can be other strategies that we can adopt? There are several strategies ranging from injecting fresh water into the underground, using ecosystems, creating wetlands in order to increase infiltration, using nature-based solution areas, so that the water that is collected by the roofs, the water that is collected by the streets, under certain conditions, is not brought into the sewer system, but it's instead released into the soil, therefore, again, favoring infiltration. And also, you can build barriers in the underground, diaphragms, which can be built of material with limited permeability, which create barriers that avoid saltwater intrusion. And these are some examples. Some of them are listed here. And other strategies may be to limit the groundwater withdrawal. And here there is a table in my website that provides a summary of the different interventions that you may adopt. There is a lot of literature which you may consult, and I may give you the example of what has been done in the Adriatic Sea, into the coastal area of Ravenna and down to Rimini, Riccione. And what they did, they decided to limit the groundwater withdrawal. And in order to get to target, they built a reservoir, an artificial reservoir into the mountains for feeding the water supply system with fresh water that was coming from the mountains, so preserving groundwater. And also they use monitoring systems in order to carefully monitor the situation, because of course it may happen that they need to use groundwater anyway, because for instance during droughts the artificial reservoir is not working anymore, and this means that they need to carefully manage the intervention and carefully manage the water use. I would say that this is everything that I may say about this topic, and please get prepared for the exam to study this proof. I'm going back on the equilibrium in order to determine the position of the groundwater surface water interaction. I go back, this one. What I did in the graphic blackboard, basically. Okay, I think this is, as I said, what I could say. And let me now, very briefly, do you have any question first? Just 1 second, I look at the chat. I don't see any question. I see a 4th student now. I'm not sure if you are connected, Faudi Rogera Cadilla. If you could complete, if you didn't do that before, the survey of the students' opinion, I would appreciate that very much. It's open up to 9 p.m. tonight. In the chat, you find the instructions. Okay. Let me now jump quickly to the last lecture. And this is, again, a very descriptive lecture, which I would like to briefly introduce, and then I leave to you for your independent study. It's a lecture that is focused on the nature-based solution for coastal protection. And nature-based solutions are very popular nowadays because they refer to the sustainable management and use of nature for resolving some of the challenges related to management of coastal areas, which we discussed. And challenges also induced by climate change and over use of the land, which means limited sustainability of human interventions. The problem of nature-based solution is they are very attractive. They are an interesting option. The problem is that to size them, to design them, it's not easy. It's not easy because they are distributed solutions. For instance, let me make an example. If you think of infrastructural solution like a dam, an artificial reservoir, it's very clear how much water you can store there. It's very clear what is water availability. Fine. If you consider a nature-based solution, which is, as we discussed, injecting fresh water into a well for pushing back the saltwater wedge, what is the effect that you gain? What is the amount of fresh water that becomes more readily available during summer if you inject fresh water during the winter? It is more complicated. It is more complicated because, first of all, the intervention is distributed. It's not just one. If you decide to inject water, you inject water in like 30 wells. So it's a distributed intervention, and it's something that it's difficult to quantify. And so this is the main problem with nature-based solution, that when we have to design them, we don't have technical guidelines. There is to say that the literature is progressing fast, and therefore I think it is a solution that you have to always keep in mind, and you have to stay updated on them. In this lecture, I am discussing nature-based solution for coastal protection and for limiting beach erosion. So it's not related to water resources management, but rather to contrasting beach erosion, which is the kind of hazard that we discussed in more detail. And so first of all, here there is a classification which I leave to you to read. This is something that you don't have to study, but it is useful because you get an overall overview of what kind of solutions you have available. I would like to jump, because we have a limited time before I close the lecture and before I close this, actually the subject. I would like to jump to the kind of intervention that we can use. And here there is a discussion, a brief discussion of some interventions with a discussion also of pros and cons, benefits and uncertainties. So let me start with cobble berms. Cobble berms means to put gravel over the beach, and therefore, in a way, increasing the size of the material that is composing the beach. This is intervention that is very popular. Sometimes, if you go back with your memory, you may go into a beach and see that there are some cobbles mixed with the sand. This is probably after an intervention of protection through the use precisely of cobbles. And these are also called, this strategy is also called dynamic revetments. Revetments means revetment means covering the beach with material that is more resistant to erosion. And usually with the term revetments, we mean material that is fixed. Cobbles are called dynamic revetments because actually they cover the beach with cobbles which are free to move and therefore are more dynamic. This presents the advantage that the aspect of the beach, the look of the beach is closer to natural. And it presents, of course, the disadvantage that being dynamic, it can be moved, the cobbles can be displaced by the waves, and therefore they need to be carefully monitored. And if needed, of course, we need to reinforce the intervention in some way. And in fact, if you go down, I'm just browsing, you see the strengths and weaknesses. So let's read for the example of cobble berms what these strengths and weaknesses may be. So the placement and construction are simple and less expensive than revetments, for instance. They appear as natural environments and again, less expensive. They are flexible under the attack of waves and therefore do not fail as static structures may. Small gravel or cobbles are less of an obstacle to beach access than large armored stone. They may become buried by sand during the summer, and therefore the look of the beach may be almost unaffected. Weaknesses. less protection than a revetment or a seawall. They require frequent maintenance, as material can be expected to move, as I said. Cobbles may be thrown landward during a storm, therefore originating a potential risk. Indeed, this is true. Cobbles and gravel do not provide the same recreational opportunities as a sand beach. Second example of intervention, artificial dunes. These may be created by using sand-filled bags, like geotextile bags, and they have the same function as a dune. So they protect the land from storm surges and waves and from the spray. And they may also supply sand to the beach. So they are very frequently used with some pros and cons. So, for instance, the weaknesses are that if we use geocontainers, they may be not much resistant to abrasion and may be vandalized, may be weakened by ultraviolet radiation from the sunlight, etc. Now, the next one is beach nourishment. Again, here there is an extended discussion and of the pros and cons. Beach nourishment is an interesting intervention because, you know, it looks natural, even if, for this, there are some issues that need to be considered. For instance, it's very difficult to find the sand with the same original color, because of course you cannot take the sand from the same beach. You have to take the sand elsewhere, and the color is frequently different, and therefore the nourishment looks in itself may look artificial. But still, it is frequently applied because it's very environmentally friendly. And again, here there is a discussion on the strengths and weaknesses. Let's move forward with the beach scrapping. Scrapping is very interesting, and it is applied during the winter in the beaches of the Adriatic Sea, and which, you know, they have a relevant commercial value. So what is scrapping? Basically, erosion typically takes place during extreme events, and especially because it's dominated by across-shore sediment transport, which means that it is originated by, again, extreme events which happen in short time scales. In particular, in the Adriatic Sea, they happen during the winter. While during summer, there are milder conditions that favor beach accretion. So the idea is, okay, during winter, let me take the sand back. Scrapping means precisely taking the sand back from the shore to the dune. So if you go during winter on the beaches along the Adriatic Sea, you will precisely see kind of artificial dunes which are formed by taking the sand back. And this is indeed interesting. And because in these beaches, actually, the dune has been removed in order to favor the access to the beach, in order to be able to use the forefront of the beach, and to be used by to build hotels, to build cycling lanes, etc. So during winter, in the worst conditions, in the worst weather condition, rebuilding the dune is indeed a very smart solution. There is to say that in this movement of sand, the ecosystem is destroyed. There is a very important ecosystem in the sand of beaches, and you know, of course, by moving the sand back and forth, the ecosystem is destroyed. Finally, I just want to mention the vegetation recovery. There are a couple of figures. This is an example of vegetation recovery over a dune, which is something that it's a nature-based solution that is becoming increasingly popular. So this is the same place. You see the picture that is taken before and after the recovery of vegetation. Okay, I would say that that's it. This is very descriptive, so it is something that typically it's not asked at the exam. Now, for closing, I just would like to take 5 minutes of your time to discuss some more about the exam. And let me stop recording.